In this presentation, we're going to be talking about the science surrounding timbre. When we're talking about timbre, we're frequently invoking the idea of the color of sound. We're likely already familiar with hearing teachers or coaches discuss tone color or use similar phrases to approach this sort of ephemeral aspect that's difficult to talk about sometimes. It's going to be important to have some basic level of understanding of what creates the sensation of timbre and why our brains process different instruments as having different colors of sound. It's really going to help inform our study of orchestration. It's not only going to help us in our artistic application of what we learn, but there will also be some practical considerations that will be a little bit easier to understand once we have a grasp on this background information surrounding timbre. For instance, understanding string harmonics, trombone slide positions, instrumental doublings, etc., etc. First, we'll review some aspects of waves, just very briefly, and then discuss what aspects of these waves our brains process as timbre. Now, we'll be referencing some science and mathematical terms. There's going to be other videos out there that take a deep dive into this science. I'm going to be offering sort of a smattering of a review so that we have some base level understanding before we jump into this larger study of orchestration, which is more our focus than specifically the science side of things. But hopefully it will give you enough of a background that you feel comfortable discussing and understanding a little bit more how timbre is working. So first, let's review waves a little bit. So sound travels in waves. It's created by energy vibrating matter, in this case usually air, around us. But of course it can vibrate solid matter or it can vibrate liquid matter. But in this case we're mostly concerned with gaseous matter, so the air that surrounds us and how the waves are traveling through. When we're discussing waves, we'll often mention frequency and amplitude. A wave's frequency is the rate at which it completes one full cycle, one full pattern of itself. That is, the length of time it takes to get from crest to crest, or from trough to trough, from high point to high point, or low point to low point. The faster the wave completes this cycle, the higher the frequency, and the higher our brains are going to interpret the pitch. A wave's amplitude is measured by the height of the crest. The higher the crest, the bigger the amplitude, and the louder we perceive the sound. Essentially, we experience frequency as pitch and amplitude as volume or loudness or intensity. So just as some background for some terminology, pitch or frequency is measured in hertz or cycles per second. These terms are interchangeable. And the range of human hearing usually extends in youth from around 16 hertz, that's C0 or 1 octave lower than the lowest C on a standard piano, to as high as 25,000 hertz, that's around G10 or 3 octaves higher than the highest G on the piano. As we get older, that tends to collapse with the high range really getting shaved off there. Loudness, which is intensity or colloquially volume, is measured in decibels, ranging from 0 decibels, barely audible, the threshold of hearing, to 120 decibels, the threshold of pain. Going all the way through from leaves rustling to airplane propellers, just so that we're familiar with some of that terminology. But let's dive back into the aspects of waves that impact timbre. So the wave we've been using as a model in these pictures is known as a sine wave. You might recognize it from pre-calculus or calculus or any sort of math or science class you might have had before. It is, for all intents and purposes, essentially completely regular. There is no variance in its amplitude or frequency. And if you listen to a sine wave, you'll hear that it sounds very sort of pure and cold, that it has a very sort of little timbre to it. It has very little color to it. It certainly does have some color, but some of the richness and complexity that we might expect from a live instrument is not there. And that's something to emphasize, that usually live instruments cannot produce a sine wave. Some of them can get close, as we'll find, but sine waves can typically only be produced artificially, that is by computers or synthesizers. Waves in nature tend to look a little bit more squiggly, like this other one here. They do not appear with this sort of regularity. Because of organic, quote unquote, imperfections, objects which create sound waves, instruments, vocal cords, etc., will produce extra resonances, that is, other waves, which combine to make a more complicated waveform. So these irregular waves that are within sort of the base wave set up a special resonance pattern known as the overtone series. So let's talk about this, because unpacking this is really going to help us understand what makes timbre timbre. The overtone series is created by the additional resonances that are vibrating within a given pitch producing wave. So here we have the first through fifth, what are called harmonics of a vibrating string. We'll talk about what harmonics are in just a moment. So these harmonics, let's assume that this large wave right here that's vibrating, this is part of a sine wave or part of a sine wave shaped pattern, and we can imagine it's extending out like that. So imagine that this is the bass wave. This is the note that you are playing on an instrument, whether it's a saxophone, piano, whatever it might be, as long as it's a live instrument, acoustic instrument. So we've got this bass pitch, what will be called the fundamental. And if it's a naturally occurring acoustic instrument, we've got then these overtones that will be created, these waves inside this fundamental wave that are going to be set up resonating. You'll notice these waves occur halfway through. The ratio is 1/2 the size of the fundamental. The next level up, there are waves that occur at 1/3 the length of the fundamental, and then a quarter, and then a fifth, and then it goes on and on and on, ad infinitum. In this other picture, we see all of those waves combined together. In this first picture on the left, they are sort of pieced apart. In the picture on the lower right, they're all sort of squished together. That's more sort of what we should visualize what's going on in a wave, because all of these things are happening at the same time when we're playing an acoustic instrument or when we're singing a pitch. So this bass wave, as I mentioned, is known as the fundamental. For all practical purposes, this is the note that an instrumentalist plays when they read a pitch. I say instrumentalist, but this also applies to singer when they sing a pitch and they hold that pitch. We're talking mostly about instruments coming up, so sometimes I'll just be referring to instrumentalists right now. The smaller internal waves that are the harmonics or overtones. So here we have this fundamental note, and here we have the overtone series that's created on top of it. It's worth noting that this goes on and on and on into infinity. It just gets harder and harder to hear. The decibel level gets smaller and smaller until we don't even really hear it anymore. So here's the fundamental note. The notes that are occurring above this, that are set up by this resonance, are known as overtones because they occur over the harmonic. And they're also referred to as they occur over the fundamental. They're also referred to as harmonics. The other word to describe these pitches is partials, which is the set of frequencies that combine to create a sound. Note that in this case, the term partials includes the fundamental or played note. Another term for partials is spectra that you'll hear. So on one hand, you have harmonics or overtones that occur above the fundamental, and on the other, you have partials or spectra, which is a way to refer to everything within the sound, including the fundamental. Sometimes it's easy to get those confused, but you can just go back online or look in a textbook and remind yourself of that slight difference. So let's break down this overtone series, because memorizing this is really, really handy and very helpful, and I highly recommend memorizing through the 8th partial or the 7th harmonic. If you can memorize above that to the 12th partial or 11th harmonic, that's even more helpful. So the overtone series always sets up the same pattern of resonances. Therefore, it sets up the same pattern of intervals above the fundamental. Here we have this low C. Our first, the interval between the fundamental and its first overtone is a perfect octave. It will always be a perfect octave. forever and ever. And then between the next two partials, it's a perfect fifth. Between the next two, it's a perfect fourth, and then a major third, and then a minor third, and then a slightly squished minor third. And because that minor third is slightly squished, the next distance is slightly larger than a major second. Then roughly a major second, roughly a major second, slightly smaller than a major second, and then slightly larger than a minor second. It's a couple of things that it's helpful to remember as we memorize this. First, as we open up the Overtones series, note that it's creating a major triad based on that fundamental note. It's creating a major triad, but each interval is smaller than the last. So first we have an octave, C to C, then we've got a perfect fifth, C to G, a perfect fourth, G to C, and then we spell out that C major chord, C, E, G. So that can be a really helpful way to remember that. The next thing that comes into play with the B flat and the F sharp that's notated here, note that there's those arrows above that saying that those are slightly flattened. Remember that when we're looking at a piano or when we're looking at music of the common practice era, particularly later in the common practice era, there's the assumption of 12-tone equal temperament. And a tempered scale is tempered from the overtone series, meaning that we're taking the notes in the overtone series and we're shaving some down and we're boosting some up so that every note is more or less equal. But these intervals don't match 100% with the equal temperament system. The octaves will, the fifths will mostly. Once we start getting into the thirds, though, then we start moving away from the tuning that is based on the overtone series or just intonation. It's called just intonation because of the idea of a law, in this case a natural law, this natural law of the overtone series. So I would highly recommend memorizing this overtone series. I would memorize it up to this third full octave, C to C, C to C, and C to C. This is the seventh overtone or the eighth partial. If you can memorize it up through the rest of up through the 11th overtone or 12th partial, that's useful too, but really memorizing this lower area is going to be super helpful, particularly when we're looking at brass instruments and when we're looking at string instruments, particularly how to write harmonics and understanding harmonics. It's also will be useful because when we're talking about doublings or voicings, understanding the basis of the harmonic series is going to give us some insight into why certain voicings sound the way that they do. So taking some time now to memorize that, an excellent idea. So we've spent all this time talking about the overtone series. So what does it have to do with timbre and these other aspects of orchestration that don't have to do with those things, like brass fingerings and harmonic fingerings for strings? Well, this is because our ears and brain tend to combine these partials together into a packet of information. We don't necessarily hear each partial separately. We can, in some cases with training, with certain things, like with overtone singing. If we're listening for it, we can hear the overtones and the partials pop out. But usually what our ears and brain are doing is compiling these things together into a packet of information and melding that, and that's what's creating the sensation of timbre. So what's really happening in this coalesced sounds is that we have relative strengths and weaknesses of different partials that combine together to create the sensation of timbre. And what's useful is we can map these relative strengths with a variety of graphs. So here we have got two graphs. We have up here the flute waveform when it's playing a tuning A 440. So that's mostly what this wave looks like. And down here we have what's called a Fourier transformation. What the Fourier transformation is going to do is show us on the x-axis the different partials. Here we have the fundamental, then the first overtone, the next overtone, etc., 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 on and on ad infinitum. We have these different partials, and then on the y-axis, we're going to have the decibels. We're going to have how intense those different partials are. So over here, I have written out the different partials of a 440. We've got the fundamental here, the next overtone up, 1 octave higher, the next up, fifth higher than that, fourth higher than that, major third higher than that, minor third higher than that. So these are the notes that sort of are combining together to form the packet of sort of sonic information that's coming at us. But not all of them are being played at equal volume. Otherwise, it would sound really quite bright and piercing up here with this high A or this high E. Instead, we have different relative strengths and weaknesses. So you'll notice that we have the most volume, we've got the most intensity here in the fundamental. So we'll map this over here. We've got this big fundamental sound. Then in orange, we have our first overtone. It's still pretty potent, so that's going to give it a very distinctive color. After that overtone, we're really going to see it diminish as we go on, as we go into yellow, green, blue, and purple. Those overtones are really almost not there. So we start to get a real diminishing intensity in these other overtones. In fact, down here we see in this quotation, higher in the range of the flute, the energy is mostly concentrated in the fundamental and second harmonic. For very high notes, it is almost a sine wave. Essentially what this is saying is, as the flute gets higher and higher, almost all of the energy gets focused in this fundamental pitch, meaning that all the energy is focused there. There's almost no energy in the upper pitches, so it's almost like we have a sound that's approximating the sine wave. That is a wave that is producing no overtones. This is one of the reasons that a high flute or high piccolo can have such a pure crystalline sound, because everything is being focused in to that fundamental pitch, and therefore it's starting to approximate this sine wave-like sound. There's a few other examples that it's useful to talk about, and I'll have some links in the video below so that you can hear a sine wave, you can hear a square wave, you can hear some of these other things. So the difference in the intensity of individual partials can be caused by a variety of things. Differences in sound source, like the instrument, its construction, the humidity that day. All of these things can affect how things sound. The method of attack, particularly when we get to percussion instruments, we'll hear that different methods of attack will create different timbres. And the medium through which the sound travels. As I mentioned, it could be a humid day or a dry day, and that's going to impact how the sound waves move through the air. So here we have an example of this first point, which is the difference of the sound source. So a clarinet, we know, is going to sound different than a flute. Well, let's look at the Fourier transformation and see what exactly is different. In this case, there's a sort of a shocking thing in that we have a very strong fundamental and almost nothing in that first overtone. Very different from what we had seen in the flute. Then, almost as strong as the fundamental, we've got the second overtone, and then back down. Then it starts going back down and looking a little bit like the flute, but it's alternating. And this is because the clarinet acts like a closed tube resonator. And closed tube resonators produce something that's akin to what's known as a square wave. And square waves produce only odd-numbered partials, meaning the fundamental and then every other partial. And if you listen to a square wave, you can hear that it kind of sounds like a digital version of a clarinet. In fact, when people are creating synthesized instruments, what they're doing is they're combining together different kinds of computer-generated waves. So combining together square waves, saw waves, triangle waves, sine waves, and piling these on top of each other, much like we see with this Fourier transformation, so that we would have different waves at different volumes, that would combine together to create this amalgamated sound that approximates the original instrument. And we can even see that the wave kind of, sort of, the wave of the clarinet kind of sort of looks like that square wave. Not exactly, but it begins to approximate it in an instrumental medium. Another instrument that's interesting to look at as we're looking at Fourier transformations is the bassoon, because it reveals the formant. So here we have this quotation: the characteristic sound of a bassoon is influenced by a strong formant. So a formant is a frequency region where the frequency components, that is the overtones, are particularly strong, regardless of the pitch. So regardless of the pitch, this area of the bassoon is going to have a pronounced intensity. In this region, the tones are heard as highly resonant. And it is the reason that responds most readily to vibration, effectively the instrument or voice's sort of sweet range. And this is what will give some instruments a particular flavor, and indeed some voices as well. Different people's voices are going to have different formants, and that's going to be that's going to create the individualization of these different voices and different instruments. In some cases, that have these formant regions, these extra strong regions, regardless of pitch. A few more notes about timbre, backing away from the scientific side of things and more towards the subjective side of things. So the sensation of a bright tone, when we're talking about bright timbre, that's going to be created by the intensity in the upper partials in a given note when compared with the lower partials. Conversely, a darker tone is created by the relative weakness of the upper partials when compared to the lower partials. Those aren't the only things that are going on, but those are things that could help. It's also worth noting that no instrument produces the same spectra or the same waveform at all times. It obviously changes based on the breath that's going through, the intensity of a bow stroke, the intensity of a drum roll. The overtones of a pitch, likewise, will constantly be in flux throughout the duration. Nothing is perfect in nature, perfect, quote unquote, in terms of computer regular. That's a better way of describing it. What we see on these graphs are just slices of the wave in one moment in time. And therefore, various registers and dynamics of an instrument will always display different spectra. So just a few things to keep in mind. A couple other things to remember is that there is a difference between pitch and noise. So when sound waves do not create recurring wave patterns, as we've seen in the examples of waves produced by musical instruments, our ear does not translate those into a musical tone. Rather, those are registered as noise. Now, that doesn't mean it can't be used in a composition. There's plenty of noisy things that happen in a composition. The percussion section uses many things that are not creating harmonic resonances, but are still creating effects that are used in the context of a musical composition. It's also worth remembering that, going back to the fact that we were looking at slices of tones before, that different instruments have different capabilities when it comes to shaping a sound. And we can see this when we look at a given sound's sound envelope. Here we have a different sort of graph that's measuring time on the x-axis and intensity, in this case measured in decibels, on the y-axis. So the sound envelope covers a length of time, and it covers three regions: the onset of a pitch, that is the attack, the sustain of the pitch, and then the decay. So different instruments have different capabilities in this regard. For instance, a piano does not have much control over its attack. The hammer hits the string, and we have a very sharp attack with a very short sustain, unless we have the sustain pedal on, and then sort of a long decay as long as we're holding that note out. Meanwhile, a more rounded attack, for instance, something that could be performed by a clarinet, which can go from almost no sound at all niente, up through a very loud sound, can create a much more rounded graph. So these are all things that we can consider and hold in our minds as we're beginning to dive into the study of orchestration, because these are aspects that we'll refer to when we are looking at different instruments. And as we move forward and we start looking at voicings and special effects, remembering some of these the basic elements that make up sound will be very, very useful and provide us insight and knowledge into how to execute these different orchestral effects.